Hello, let's talk about center. And when we're talking about data, when we're talking about our socks, shape, outlier, and center and spread, what we can do about this center right here. So when we're talking about center, normally what we really want to know is where is the data positioned? Where is it at on a number line? How can I say where this data is? So we have three measures of center that you've used in other classes. We've talked about mean. Mean is the arithmetic average. It's what you get when you add them all up and divide by how many there are. We've talked about median. That was last lesson, where you have all the values in order and you pick the very center one or the average of the two center ones. And we have mode, which is the most frequent value. Now mode, again, we a lot of times will reference when we're talking about shape because it is the most frequent value in the data set. But for statistics, a mode tends to show up as a peak in the data. So when you have this unimodal and bimodal, what we're seeing are values that appear more often than others, and they show up as peaks in your data. When we're talking about mode, a lot of times we're using categorical data. When we talk about the most frequent category or the least frequent category, we're talking about mode. Our other favorite one down here is, besides median, we've got the mean. So a couple new symbols for AP statistics here. When we are talking about mean, we have two symbols that we use based on whether or not we're talking about a population or a sample. Okay, so the first one is, we've talked about before too, it's X bar. So we would read this, it's an X with a little line over it, and we read that as X bar. The other one is this Greek letter right here that kind of looks like a fancy M, okay? And this is the Greek letter, which is pronounced, I'm going to write this like it's a little cat here, mu, like a little cat, mew. Okay, so we have our X bar, which is the mean of the sample, and mu is the mean of the population. So again, in statistics, we tend to use English letters for sample values and Greek letters for population values. So the idea is, if I was going to talk about the average height of a sample of 14 Avon High School students, I might say X bar equals whatever. And if I had the height of all Avon High School students from their medical records or something, then I would say mu equals that number. Another little thing that we got to look out for is the number of observations. So N is typically our sample size. So a lowercase n stands for sample size. And then we use a capital letter N to represent the number of observations in a population. So that would be our little n is 14 students in our sample, and capital N is the 3,000 students at Avon High School. All right, now to compute these, this is fancy English here for X bar and mu here. They have the exact same formula, and you're going to see this other little sigma here, this little summation symbol in the numerator, and the number of values. So there's nothing fancy about this. This is exactly the same way you've found a mean, and found an arithmetic average your whole life since, fourth grade. This X bar, this sigma X stands for the sum of all the X values. You basically add them up and you divide by how many there are. Same formula for both. You add them up, you divide by how many there are. When you go to do these problems, though, one thing that you might be asked to do is to interpret the mean. What does the mean mean? What is this value? Okay, so the typical sentence that we're going to use is we're going to say this number, 60.5 inches, is a typical value of height of Avon High School students. I guess that'd be pretty short though, wouldn't it? But this idea of it's a typical value of our variable. So you want the number that you calculated with its units, and you want to say it's a typical value of whatever you calculated. And it's not a bad idea to put in also if it came from a sample or if it came from a population. All right, so for example, students were asked to estimate the incline angle of a ramp leading up to a loading dock. A sample of the responses are given below. Find the mean. All right, so I've got 59, 49, 64, 49, etc. So what we would do is we would take all of these numbers and we would add them up. Okay, I know this is a sample, and so I've got an X bar here. X bar is, they add up to 489. I already did that in my calculator. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 values, so divided by 9, and I get 54.33 degrees. So, two things to note. First off, this is annoying, but it's true. You need to show your work. Yes, I know that you are capable of adding all of these numbers up and dividing by how many there are in your calculator without showing your work. I'm going to tell you it's always better to show that original fraction setup. It's always better to say 489 over 9 and then go ahead and type in your answer, that 54.33 degrees. So when we use the one variable statistics in the TI Inspire, you may remember that right under that X bar value was the sum of X. So you can use that to set up the fraction. Sum of X, you know what that number is, divided by the total number equals your X bar value. Okay. The other thing is that we need to be able to interpret this. If I say interpret the mean, tell me what the mean means. I would say 54.33 is a typical value of the variable, estimated incline angle of the ramp for this sample of students. Okay, so for this sample of students, 54.33 is the typical value of this estimated incline angle of the ramp. Now, sometimes when we go to do a mean, we may have lots of answers over and over that are actually the same thing. So one thing we may want to do is do the mean of a frequency distribution. So for example, students were asked to report the number of hours they spent studying for an upcoming test. They were allowed to choose 0, 1, 2, 3, or 4 or more. And the results are shown in the table. So over here in my table, and I've already done quite a bit of work already on this one, so I wouldn't have to write it while I was talking. There was 1 student who said 0, 3 students who said 1, 7 students who said 2, 1 student who said 3, and 1 student who said 4. Now there's no reason why you couldn't just say 0 plus 1 plus 1 plus 1 plus 2 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 plus 3 plus 3 or plus 3 plus 4. Add them all up and divide by how many there are. You could do this just like this previous page, but it's really slow. Okay, and if you get an idea of what this looks like, I've got a little histogram over here. If I was going to ask you to estimate the number of hours, like what was the typical number of hours, it looks like somewhere around 2. Okay, that's where that peak is showing up. It looks like it's fairly balanced on either side, maybe a little less than 2. If we were to average out, it looks like there's a few more 1s and 0s than there are 3s and 4s. Okay, so it's not exactly balanced, but it's pretty close. So somewhere between 1 and 2, closer to 2 probably than 1. Okay, so I can kind of see this on my picture. So what I'm going to do to kind of do a shortcut of this is instead of adding them up individually, I think, okay, I've got 1 0 and I've got 3 1s, I've got 7 2s. So essentially we're doing a multiplication here. Instead of going 0 plus 1 plus 1 plus 1, I'm going to do 0. 3 1s would give me 3. 7 2s gives me 14. 1 3 gives me 3, and 1 4 gives me 4, and those add up to 24. So 1 0, 3 1s, 7 2s, 1 3, 1 4, that gives me a numerator here of 24. And then also, how many numbers do you actually have? It's really tempting here to say that you have 5 numbers. What you do is you have 5 different responses. But again, 1 person said this, 3 people said that, 7 people. So there's actually 1 plus 3 plus 7 plus 1 plus 1. There's actually 13 responses in this data set. Remember, you want this number, when you're looking at the picture, you know the number ought to be somewhere around 1 to 2. So if you did 24 divided by 5, you're going to get an answer that's like 4 point something. That's not going to make any sense at all. So remember, when you're arithmetically doing things, to always look out for, does that actually make any sense at all? If it doesn't make sense, you probably got an arithmetic error in there somewhere. Okay, so 24 divided by 13, I already punched this into my calculator. That is 1.85. 1.85. And if I look over here, that would be somewhere here-ish. That makes sense. That's a nice, that makes sense as the value of the mean. That would sort of balance the data on either side of this. So if I was going to interpret this, then I would say 1.85, and I'm looking for my unit here. What is my unit? The number of hours. 1.85 hours is a typical value, or is a typical value for number of hours spent studying. In this sample. Oh, I ran out of room to write it. Sample. There we go. So 1.58 hours is, or 1.85 hours is a typical value for the number of hours spent studying in this sample. So that's how we want to think about the mean as a typical value of the variable. The idea of a mean and a median, both of them, is that you're trying to come up with one number that represents the whole data set, that kind of gives you an idea of what that data set means. Okay. All right. Now, another thing that sometimes you may see happen is you may be asked to do something called a trimmed mean. Trimmed mean is kind of like when we say, hey, you know, we really want to get the central value here, but we got a few really high and a few really low that we think may be, you know, affecting our data more than we want. So in a trimmed mean, what you do is you basically take your data set, pretend like that's a whole bunch of numbers lined up in a row, and you trim off both sides. You trim off the low extremes and you trim off the high extremes, and then you find the mean of what's left over in the middle. So if we're trying to find this typical value, we may say, you know, these extremes on the other end, they don't really represent what we think they're representing. All right, so to do this, what you do first is you determine your sample size, and then you trim off, you compute how many values would be a certain percentage of trim. Okay, so for example, you have the following grades so far in AP Statistics: 100, 92, 28, 87, etc. There are 10 values here, 1, 2, 3, 4, 5, 2 rows, 10 of those. So to find the mean, again, I would add these all up. All right, so what do we have here? Let's see, 100, 92, 28, 87, 89, 75, 105, 72, 83, and 83. That looks like 814. 814. All right, 814. I'm going to divide by 10, and that gives me 81.4. So that's your mean grade right now, is an 81.4. Okay, so I'm going to offer you the following deal. I am going to, you can either take this grade as your average test grade, or I will calculate a 10% trimmed mean. All right, so to do a 10% trimmed mean, the first thing we need to do is figure out how many values is 10% of our sample. So I take 10% of 10, or in other words, my trim percentage times the number of values. 10% of the trim is 1, but I'm going to not just knock off the highest one, I'm also going to take off the lowest one. So I go look at my data, the very highest number is this 105, and the lowest number is this 28. So now, instead of having 10 numbers, I've only got 8 numbers. I'm going to find the trim of what's left over. So 100 and 92 and 87 and 89, 75, 72, 83, and 83, that adds up to 681. And if I divide by 2, or divide by 8, I get 85.125. So I should definitely take Mrs. Leahy's deal, right? Because if I do the trimmed mean, by dropping that highest and lowest number, I actually end up with, even though I had to drop a 105%, that balanced out that 28% quite a bit and actually raised my overall average. Now, some people will ask, well, what if I had, 320 test grades? Well, 10% of that would be 32. I'd remove 32 top scores and the 32 bottom scores. What if it comes up as a decimal and it tells me I need to remove 2.7 values? Well, then take off 3 from the top and 3 from the bottom. What if it's 1.2 values? Well, then decide. Take off 1 or 2 from both sides, depending on that, what makes most sense in your context there. All right, so when we are talking about mean and median, then both of these can be used as a measure of center, but they have a different kind of value. Okay, so a lot of times what happens is when you have a mean and a median, if they are not the same, it's indicative that your data may have some extreme values on the end, or that the data may be skewed in one direction or the other. When you have a very, very high value, your average tends to get pulled in that direction. So if you've had 10 test scores that are, say, 75s, and the next test you get a 110, it's going to pull your average up. It's going to bring that average up. It's going to bring that mean value up. Okay, but the median would still stay the same. You have a bunch of 75s and one high score, still going to be the same in the middle. Okay, same thing as if you had a whole bunch of values that are around like 75, and then you come in one day, have a really bad day, score a 20%. That 20% is going to drag your average down. Okay, so I've got these two samples here. Sample 1 is the numbers 1, 2, 3, 4, 5. Okay, if we were to add those up, that's 15, and 15 divided by 5 is 3. If I look at the median, these are in order. My median is my middle value. That's also 3. So those are really close together. Now, what I would look at that and I would say, if the mean and the median are about the same value, then what's most likely happening here is that this is a symmetric or an approximately symmetric distribution. Now, I don't know for sure. This is just me making a guess about what I'm seeing. But typically, if your mean and median are the same value, it means that your distribution is most likely symmetric or approximately symmetric. I go over to sample B and I've got 1 plus 2 plus 3 plus 4 plus 500. Okay, so that's a really big number over there on the right. Okay, I add these up, I get 510, which gives me an average of 102. All right, so the mean is 102. That is much larger than it was before, but now the median still 3. So I would look at this and I say, wow, that mean is a lot bigger than that median is. So the mean follows the skew. So if the mean is on the right side of the median, then that means that the data is skewed to the right, most likely that distribution. Okay, so if your mean is to the right on a number line of the median significantly, then a lot of times that is going to represent something that's skewed to the right. If your mean is significantly smaller than your median, so on a number line the mean is to the left of the median, then the mean follows the skew. That means it's probably skewed to the left. Okay, so if I had to make a guess just solely based on these two values, what would I think? I would guess that this shape would be approximately symmetric, and I would guess that this shape would be skewed to the right. So you can often make a really great guess about the shape of the distribution even without looking at the graph there. Okay, all right, now being true then, resistant statistics, this word resistant statistics, these are ones that are not affected by extreme values. If you add an extremely large or an extremely small data value into your data set, it's not going to change that statistic back and forth. So things like median and interquartile range, median and interquartile range are literally just focused on those center values. And if you make a change on one end or the other of the data, it really doesn't change the position or those center values very much. It might move it just a little bit, might expand it just a little bit, or decrease it just a little bit, but those don't change very much. However, like the mean, if you drop a big value like 500 into your data set, your mean is going to jump up significantly. The same thing's going to happen with standard deviation and range. Now we'll talk more about standard deviation in section 4.2. But the range, if you think about that, here's your range, and then suddenly you add in a great big value up at the end of the data, that's going to increase that range and decrease that range. So the interquartile range, which is in the middle, that one doesn't change very much. But the overall range or standard deviation, we talk about that, those are non-resistant. They are not very good at holding their values. Okay, so things about means and medians then. The mean, reasons why we like it. Pros for the median. First off, the ultimate reason why we like the mean more than other measures of center is primarily because it uses all the data values. Every data value is included. High numbers, low numbers, medium, like everything is included in that calculation. You add them up, you divide by how many there are. There's also a formula for it. Okay, it's defined by a formula. We like that as mathematicians. The cons of using the mean. The mean is often distorted by outliers. It's distorted by skewness. If I look back at I have a whole bunch of kids and they got a 75 on a test. I got one kid who has 100. My average is going to be higher than 75, and it could be that arithmetic average is not really hitting the idea of a typical value of the variable. So if you have a data set that's got a lot of skew, or if you've got a data set that's got a lot of outliers, the mean is supposed to represent a typical value of the variable, and that mean might be too high or too low to be really doing a good job at that. Now the median though does a great job at that. If you've got it skewed or it's got symmetry, it's not distorted by outliers, it's not distorted by skewness. That's fantastic, but it also ignores almost all of the data in the problem. It does tell you the central value, but it doesn't tell you anything else besides what's right in the middle. And so you could have two data sets that are very, very different that still have that same central value. It's not algebraically defined. It sort of has this subjective definition. So it's not really our favorite one to use. Okay, so the idea here is if you have to choose between mean and median, if the mean is reasonable, this is our first choice. Okay, so if you have a data set that's not highly skewed or does not have a lot of outliers, you want to use the mean as your measure of center. If you have a data set that does have a lot of skew, it does have a lot of outliers, it's probably going to be better to use the median as your typical value. All right, so how do you decide? You're going to start when you talk about your socks, you're going to start with shape. That's why shape is first in socks. What is the shape of the data? And it's going to tell you which measure of center and spread are the most appropriate for your data set. If you have a data set with a very strong skew or with a lot of extreme values like those outliers, it's probably best to describe center using median. Median is probably your best choice there. Okay. When you talk about median, you're going to use your interquartile range as your measure of spread to go with it. If you have a distribution that's symmetric or it's not too skewed, the outliers aren't too extreme, okay, then it's best going to be described using the mean. The mean is our best choice in that manner, okay? Also, a lot of our distributions that we deal with in this class end up being unimodal, so it's not inappropriate to talk about that. But remember that the idea of symmetry and skew, that's what we really want to get to when we're talking about shape. Don't also forget that distributions, when you describe them, they need to be in context. Use the name of the variable when you're writing. Okay, you need to use complete sentences, and you always need to include the unit of measurement if it's continuous. Okay, so don't just say it's 100.8. Say it's 100.8 degrees, or it's 62 inches, or whatever you have any measured in. All right, so mode then is our last one. We had mean, we had median, we have mode. We usually save mode to either talk about that unimodal, bimodal part of shape, or we use it to talk about categorical data. So remember, categorical data, there's no socks. So when you see you've got categorical data, you're not going to talk about shape. You're not going to talk about outliers, center, spread. None of that applies. That only applies to numerical data. For categorical data, what we typically are going to talk about are the frequency of categories. And so one thing that we typically talk about is the proportion of success. Okay, so success could be anything. It could be actually just like we're counting success and failure, or maybe we're talking about, we gave a certain drug and we want to look for the people who improved, or we want to look for the people who declined. Success is basically whatever you're counting, whatever you're looking for. So if I'm looking for this measure of success, I want to know what proportion are successful. I need to know how many there are. Okay, so there were 15 values in this data set and there were 9 successes. Okay, so when we do this, just like with mean, where we have 2 different values, we have x bar and we have mu to represent our population or our sample. We also have the same thing with proportions for categorical data. So we have this symbolism here. It's this P with this little, it looks almost like an upside down V on top of it. This is called P hat, P hat. So P hat is the proportion of success in a sample. All right, so here's where it gets a little sketchy. The Greek letter for P is our friend pi, but the geometry people got to it first, and now anytime you guys think pi, you think 3.14, which is fine. All right, thanks geometry. Okay, but that is the Greek letter P. So sometimes when we're talking about a proportion of success in a population, we would label that as pi. So you might see like, P hat. I went to Avon High School students and I asked how many were in favor of our ID policy. I got 21%. And then if I was actually to ask every single person in the population, every single student at Avon High School, I would say pi equals 19%. That's everyone, the proportion of everyone, whereas P hat is just that sample. So what we typically do, because pi gets confusing, is it 3.14? A lot of times we just use the English letter P for this. So either one of these can be used. If you see your textbook has a tendency to use pi, okay, but a lot of times P is just our population proportion. So to compute this, again, you just take the number of successes and divide by the total. In our case, that would be 9 out of 15, which would be 60%. Okay, generally we would express a proportion as a decimal or a fraction, okay? And I don't normally see a really good reason for writing it as a percentage unless you're specifically asked in the problem for a percentage. Otherwise, just leave it as the fraction or just leave it as that decimal. So again, P hat is the proportion of success, which means if you did 1 minus P hat, that would give you the proportion of failure. If I know 20% were successful, that gives me 80% of failure. You can also use subscripts, and we'll do that in later chapters to show different proportions, like the proportion of vanilla, the proportion who said chocolate, the proportion who said strawberry. That could be like P hat 1, P hat 2, P hat 3. You can do that with subscripts. All right, so for means, you need to know how to calculate a mean and interpret it using a complete sentence. The typical value, units of the variable, okay? You need to know how to find a trimmed mean and the mean of a frequency distribution. Okay? You need to know how to calculate a proportion of success, and you need to know when I'm looking at the mean and the median, what do the values of mean and median tell me about the shape of the distribution if I don't have access to that information?